Hi everybody. So welcome back for another lesson. Today we're going to be looking at the fundamental theorem of line integrals. Alright, so what I want you to do really quickly is I want you to recall back from Calc 1 where we had this fundamental theorem of integrals. And this fundamental theorem of integrals basically said that if we can take a definite integral from limit bounds a to b for this antiderivative, or sorry, for the derivative of some function, then when we take the integral, we're basically undoing that process. And in doing so, we get to evaluate the initial function at f of b and f of a and just subtract those two values. All right, now that was pretty good and pretty straightforward back in that time, and we want to look at the exact same process here. That when we're still looking at some curve that's a smooth curve, and it's going to be defined by this vector parametrized function on some given t interval, and if f is a function whose gradient vector is the gradient of f, and that's going to be continuous on the curve, then again, naturally what should happen if we took a derivative and then we want to take the integral, we should still be able to do the exact same thing that we did back in Calc 1. We should just be able to evaluate the function at this given value and the function at this given value and then subtract the two. Alright, so this is what we're working with for now in this particular section. There is going to be more to this section than just a fundamental theorem of line integrals, but again, we have to start with this, that way we can start seeing how we're going to be using this. Alright, now on this example right down here, I have this example that says evaluate this line integral where we have this gradient of f, and we're going to evaluate it with respect to r, and the function in question is this function here, and c is any path. So I want you to pay attention to this. This says that c is any path. Alright, so c is going to be any path as we're going to be moving through this specific vector field. But if you notice, this vector field is really a gradient vector field because typically this in here is f. And remember, if we said that if we have some vector field function equaling to its gradient field for a different function, then we have a potential function of this vector field. And that's exactly what this is. And so since we have this potential function, what we're basically going to be doing is that we're going to be figuring out what this evaluation is for any of the paths that are moving from this point to this point. Alright, so in here, what I'm going to do is I'm going to use the fundamental theorem of line integrals. Excuse me here. Alright, so I'm going to be using the fundamental theorem of line integrals here. And the fundamental theorem of line integrals, I'm going to have c, and then this is going to be del f dr, just like this. Alright, now again, all I need to do is I need to figure out then what is my gradient field here. Now, what is a gradient field again? If we had the gradient field, then that's awesome. But at this particular time, we don't really need it because if we notice, again, taking the integral and the derivative kind of like inverse operations of one another. Which means all we really have to do at this particular case is just evaluate the function at these given points. Alright, so this is going to be treated as, say, point A, and say this is going to be treated at, let's say, point B. Alright, so when I do this, I then want to find, well, what is going to be this function evaluated at, well, some vector position function. We don't know what r of t is. At the end of the day, we don't need to know because this is going to be any path. Alright, so as we start going through this, we're just going to say, okay, well, the path is going to lead us to this endpoint, and naturally, if we had that path, then we would just end at that point if we were given a vector position function. And we're going to subtract it by the point where we initially started, 1, 1/2, and 2. So all we need to do is just make our substitutions. All right, here we go. So this is going to be cosine of pi x. So that's going to be this piece here. So that's going to be cosine of 2 pi plus sine at pi y, and that's going to be 1. So that's just sine of pi minus xyz. So minus x times y times z. That should be just negative 2. So that's going to be positive 2. There we are. Minus function evaluated at this point. All right, so it's going to be cosine at pi plus sine at pi y, and pi y, that's going to be this guy right here for y, so that's going to be sine of pi halves, there we are, minus, and then we're going to have this point here for x, y, z, so x times y times z, so that's just going to be minus 1. There we are. Now we can go through and start evaluating here. All right, so cosine at 2 pi, that should be a 1. Sine at pi, that should be a 0. Then we got plus 2. Then we got minus cosine at pi should be negative 1. And then sine at 2 pi, that should be 1. And let's distribute that minus, so it's going to be minus 1. And then we have here minus 1. Perfect. All right, so making sure all my distributions went through negative, negative, negative. Awesome. So this is going to be 2 plus 1. So this is 1, 3, 4. All right, it's looking good. So it's going to be 4 and then minus 2, so it should just be 2, if I'm not mistaken. And again, we can double check our work here. So let's see, I got 2 times 2 times 2. Perfect. 2 times a half. Nice. That's 1. Alright, looking good. Sine. Oh, excuse me. Yep, there it is. Okay. My apologies. I see there's a mistake simply because that needs to be a positive. My apologies. When this distributes in, that's a positive, which means these last two ones cancel and we should just get a value of 4. There we are. Everything's nice and neat now. Perfect. All right, so this is how we want to use line integrals. All right, now one of the biggest aspects is how can we identify that we can use a line integral like this to evaluate a line integral, right? When can we apply this fundamental theorem of line integrals? That's one of the big questions that arises from this. Now, one of the things that we're going to be investigating in this section is how to find these functions right here so that when we're looking at this type of line integral and we have a vector field given to us, how do we know that we can then evaluate it using this fundamental theorem for line integrals? All right. So in order to do that, or in order to investigate that, we need a lot of definitions. All right, so I'm going to go ahead and I'm going to write a lot of definitions on here for you guys. All right, there's going to be about 7 of these definitions that we need. All right, and then after that, we're going to move forward and we're going to start identifying some of the theorems that we're going to need in order to tie all of this in nice and neat. All right, so bear with me. I'm going to write some definitions on the board and then we'll get to it. All right, so here's the definitions that we're going to be working with. Now, here we have at the very beginning, it says, suppose that F is a continuous vector field in some domain D. All right, so all of these domains that we're looking at here are going to be inside of some continuous vector field that we're going to be observing. All right, definition 1 says that if F is a conservative vector field, then there must be a potential function that we can identify that's just going to be the gradient of that potential function is going to be equal to the actual vector field itself. All right, this definition we actually got early on back in the beginning parts of chapter 16. All right, so this kind of gives us a way to determine, hey, can we find the potential function if we know that the vector field is conservative? All right, so that's number 1. Number 2 here says that we are going to be looking at something called independence of path. So if we have two different curves, and I gave you a small depiction over here on the right hand side, that if we have two curves, call this C1 and C2, where C1 and C2 have the same starting point and the same ending point, then if this is independent of path, the two integrals, the two line integrals for that vector field through those different curves must be equal to one another. If they're equal to one another, again, we're going to say that this is independent of path. And if it's independent of path, meaning that it doesn't matter which path we could take path C1 or path C2, and we're going to get the exact same evaluation for that line integral. All right, so that's what independent of path tells us. Number 3, a path is called closed if its initial and final points are the same point. So on here I drew just a path here in blue where I have point A and point B. Point A is your initial point B is your your final point. Start at point A, you traverse the curve, and you wind up right back where you started. This is a closed path, all right, otherwise known as a closed loop. Number 4, a path is simple if it does not cross itself. So here I have two depictions. Simple path here is just a path starting. It doesn't cross itself at all. Starts at one point, ends at another. Here's a different path. Starts at one point, keeps moving, but it crosses itself and then it goes over to its other point. This is not a simple path. All right, number 5. A region D is open if it does not contain any of its boundary points. All right, so here I drew some region D, and the region is the part that we're bounding here, but notice I drew the boundaries dotted or dashed, which means that the region does not take on its boundaries. All right, nice. So that's how we're going to define open on some region. 6, a region D is connected if we can connect any 2 points in the region with a path that completely lies in the domain D. So can we find 2 points and then can we connect them with a path that lies inside of the region? All right, that's the only stipulation. All right, now if we can, great, then that region is going to be connected. Now remember, we're trying to do this so that the region D is inside of some vector field, and these paths that we're looking at are going to be the curves that we want to be integrating over. Finally, number 7, a region D is simply connected if it is connected. So again, it has to satisfy this definition up here, that it must be connected and it must not have any holes. So here again, you're going to see two depictions. One depiction is going to be the first region that is simply connected. All right, it has no holes within that region. However, the second region here, this does have a hole right in the middle of its region. This is not simply connected. All right, so these are the definitions that we are going to be working with in chapter 16. Any type of problem that references any type of independence of path, simple, open, connected, simply connected, will then rely on these definitions here. All right, so we do have to know them. However, I will not have you recite one of these definitions, or I will not have you write one of these definitions on an exam. I only want to know, do you understand what these definitions say, and do you understand how we can implement them within our work? All right, so now that we have all these definitions, now is going to be some time to develop some of these theorems that we're going to be working with. Because all of these definitions actually help us generate a whole bunch of theorems that we can then start applying to these conservative vector fields, or how to find these conservative vector fields. All right, so we're going to start listing some of these theorems next. All right, so here are the 5 theorems that we're initially going to work with and talk about. So the first theorem that we look at is that if we're looking at a closed integral, or sorry, a line integral, excuse me, if we're looking at a line integral, and I just realized I made a fudge here. So if we're looking at the line integral for a potential function with respect to dr, then this is going to be independent of path. And again, what this is saying, this is telling us that we're working with a gradient vector field. If this is a gradient vector field, then we're already looking at some potential function that we can look at, which means that we're dealing with a conservative vector field. And that's what number 2 is really telling us, saying that if you have a conservative vector field, then when you take that line integral for that vector field, then it's going to be just independent of path. All right, so kind of 1 and 2 make kind of like that if and only if statement for this theorem. Number 3, if f is a continuous vector field, all right, so here we have a continuous vector field, and it's going to be on an open connected region. So again, there we have that definition for open connected. All right, so it's going to be open, doesn't contain any of its boundary points, and connected means that we can draw any two, we can connect any 2 points with a path that lies completely inside of that region. All right, and if the line integral is independent of path, then we're going to have that the vector field is a conservative vector field over that region D. All right, the next one, if we have this line integral being independent of path, then when we take the line integral over any curve that we can find, it must be equal to 0, and this is only going to hold for every closed path. All right, so we got to be very, very careful there, that when we're talking about closed paths, and we have these line integrals that are independent of path, well, if you look at theorems 1 and 2, independent of path means that we're going to have some conservative vector field, so that when we take a line integral for any closed path on that conservative vector field, the line integral should always be 0. All right, kind of like looking at displacement, you're right back where you started. So if you started at one point, you end at that point. Displacement would say you haven't moved anything, but total distance would actually say something different. All right, number 5, if we're looking at the line integral over any curve for that vector field is equal to 0 for every closed path, then we're going to get that the line integral is independent of path. And again, if it's independent of path, then we're going to have this conservative vector field that we're going to be working with. All right, so these theorems are to help us identify when are we working with these conservative vector fields. If we have a conservative vector field, then that's going to be awesome, because again, at the end of the day, we can go back and we can start using the fundamental theorem of line integrals, which makes everything really nice, neat, and concise. All right, so these are the theorems that we're going to work with. Now, how do we identify a vector field to be conservative? All right, that's going to be the next theorems that we work with. We want to make sure that we can identify when these vector fields are going to be conservative. So let's go through and let's start applying that process, and we're going to see how that process is once we get these theorems going. All right, so here's the component test for the conservative vector fields. All right, so if we're looking for a conservative vector field, what we're going to do really quick is we're just going to define some vector field that we're given in terms of a three-dimensional component. So we have some m, n, and p functions that are all comprised of x, y, and z's. All right, and this is going to be a vector field on an open, simply connected domain. All right, so again, here goes those definitions that we're working with: open and simply connected. All right, whose component functions have continuous first-order partial derivatives. Then we're going to be able to say that we have a conservative vector field if and only if these partial derivatives for their individual components with their respective differentials with their variables are equal to one another. All right, now this definition here in blue is for this continuous vector field in R space 3. What if we had a vector field in R space 2? If we had a vector field in R space 2, then I'm just going to define this two-dimensional vector field P's and Q's, and we're going to have these components must be equal to one another. if this is going to be a conservative vector field. This IFF stands for if and only if. It is shorthand notation for if and only if. We just write IFF. All right. Now, the big question is, how do I memorize this, right? And here's the big thing is that I haven't really memorized this. I just know how to derive all of this. All right. So here's what you want to look at when you want to kind of derive this. All right. If you remember, we worked with determinants. And these are this is a determinant that we typically worked with. And what I'm going to do is on the bottom row, on the first row I have my unit basis vectors, I, j, and k. My bottom row I'm going to go with my functions. This is going to be m, n, and p. All right. And in my second row, what I'm going to do is I'm going to insert my operators for my partial derivatives. So this is going to be partial derivative of something with respect to x, partial derivative of something with respect to y, then partial derivative of something with respect to z. All right. And what I want to do at this point in time is I just want to go ahead and get the determinant for this particular matrix. So I'm going to go in the I component. In the I component, we're going to have the partial of p, because again, I'm multiplying these two. So it's going to be the partial of p with respect to y, minus, and then I'm going to subtract out the minor here, and that's going to be the partial of n with respect to z. There we are. And then minus, all right, I'm going to do my minus. I'm going to do the minus here. So minus the j component. The j component, that's going to be the partial of p with respect to x. There we are. Partial of p with respect to x. Minus, and again I'm doing the j component, minus the minor row in here, partial of m with respect to z. And then I'm going to do the plus k coordinates. So the k values is going to be partial of n with respect to x, minus the partial of m with respect to y. Now, what I want you to notice here, what would happen if we set each individual component to 0? So if we take this component, set it equal to 0, this component, set it equal to 0, this component, set it equal to 0. Well, if we set it equal to 0, then we naturally get the partial of p with respect to y minus the partial of n with respect to z being equal to 0, which means we get the partial of p with respect to y is equal to the partial of n with respect to z, which is this very first piece that we have. Notice if you set the second one equal to 0, again, you get the same thing. Set the third one equal to 0, once again, you get the same thing. So why is this playing out? Why can I see this taking place here? Well, a lot of it has to do with subjects in math that we're going to be looking at, hopefully in a little bit. All right, but more than that, if we know the things about line integrals and these closed paths that we're looking at here, we have an open simply connected domain. All right, so when we're looking at an open simply connected domain, what we can start doing is saying, okay, well, if this is a conservative vector field, then what is the line integral going to be equal to? Well, the line integral is going to be equal to 0. That, according to us, would mean that every single component here must be then equal to 0, which then gives us this natural progression to say if we have a continuous vector field, a conservative vector field, then we must have this partial derivatives to be satisfied. All right, so that's how we're working with it in this particular section. And what I'm going to do next is I'm going to give you some examples to see if we can determine whether a vector field is conservative or not. All right, so here goes your example. Determine if the following vector fields are conservative. All right, so let's go with part A. For part A, I'm going to give you the vector field defined by x and y's, This is going to be x squared minus yx, and that's going to be in the I component, plus y squared minus xy in the j component. Now, the first thing that we're going to notice is that this is a vector field in R space 2. And because it's a vector field in R space 2, I'm going to use this second definition, or that second theorem that we had, to show that my vector field will still be conservative. All right, so let's go through and let's go ahead and let's figure that out. All right, so here we go. All right, I'm going to be working with this first piece. My first piece here, my first function, is going to be that p, and that's going to be this function here. P of xy is equal to x squared minus yx, and I'm going to label q of xy, that's this function, to be y squared minus xy. So in order for me to be able to work with this, I need to determine what is the partial derivative of p with respect to y. Alright, in here that partial derivative with respect to y is just negative x. Now I need to work with the partial derivative of q with respect to x. So this partial derivative with respect to x should be negative y. Now all we have to do is identify, are these two equal? Well, what can we come up with? The big answer of no. They are not equal. They are not equal to one another, which then tells us that this vector field is not conservative. So f of xy is not a conservative vector field. There we are. And that's it for part A. Right? There's nothing much to it from there. All right. Let's look at part B. For part B, what I want to do is I want to look at this vector field. Let's say f of x, y. And this is going to be 2x e to the xy plus x squared y e to the power of xy. And that's in the I component, plus x cubed e to the xy plus 2y in the j component. Alright, so now that I'm looking at this, I want to go through and I want to figure out this vector field, see if this is going to be a conservative vector field. Alright, so the first one was not, that's okay. So I'm going to go through and I'm going to identify my functions once again. My function p, this is going to be 2x e to the power of xy plus x squared y e to the xy. And then my function q is going to be x cubed e to the xy plus 2y. Nice. So what I want to do is I want to find the partial derivative for p. So I'm going to find the partial derivative for p with respect to y, like such. So I'm going to go through my first piece here, taking it with respect to y. So this is now going to be 2x squared e to the power of xy. And then for the second piece here, I'm going to need the product rule. So my product rule, I'm going to take the derivative of this first function here with respect to y. So that's just going to be x squared. And it's going to multiply e to the power of xy plus the first function, which is just x squared times y, multiplied by the derivative of the second function here. So the derivative of the second function with respect to y should just be e to the power, so it's e to the power of xy, and that's going to be multiplied by x, so we're going to have an x cubed here. Like such. There we are. Perfect. And do I see any? Yes, we have some like terms here. So I have x squared e to the xy, e to the xy. So we have 3x squared e to the xy plus x cubed y e to the xy. Nice. So here's my first partial derivative. Got it. Let's work with the second partial derivative. Partial derivative of q with respect to x. Of q with respect to x. Alright, so again, I'm going to need the product rule here for the first term. So using the product rule there for the first term, I'm going to take the derivative of the first function which is 3x squared, all right, multiplied by the second function, e to the xy, plus the derivative of the second function with respect to x. So that's going to be x cubed y e to the xy, and then this derivative here with respect to x, well, that's just going to be 0. Which means we get 3x squared e to the xy. Oh, hey, look, 3x squared e to the xy plus x cubed y e to the xy plus x cubed y e to the xy. Which means these partial derivatives are in fact equal to one another. Which means what we can say here is that f of xy is a conservative vector field. Yay. Awesome. So we are able to extract that we are working with a conservative vector field here at this point in time. Awesome. So let's look at one more example. Let's look at part C. Oops, excuse me. So here goes part C. I want this vector field which is going to be y sine of z in the I coordinates, x sine of z in the j coordinates, and then we're going to have xy times cosine of z in the k coordinates. Awesome. So let's go through and let's go ahead and let's figure this out as to what are the partial derivatives that we're going to be looking for. All right. Now, again, the way I want to do this, because this is a function, a vector field function in R space 3, I'm just going to go ahead and write my ij's and k's here, and then I'm going to have my partials on the second row. I'm going to have my first function, which you can label as m and p. So you can label this as m, you can label this as n, and you can label this here as p. As such. Alright. Now again, this is just going to be for my reference, so that when I work with them, I can automatically extract what I'm looking for. Alright, so the first one's going to be the I component here, so that's going to be the partial of p with respect to y. So I'm going to go with the partial of p with respect to y. So the partial of p with respect to y, that's the first one that I'm working with. So that's this function with respect to y. That's going to get me x cosine z. Nice. And then the other one that I'm going to be working with, let's see, that's going to be partial of n with respect to z. So partial of n with respect to z. All right, here we are. That's going to give me, let's see, x cosine z. So far, so good. This is in fact equal to one another. Great. All right, so the I component's done. Awesome. So that's one of them. Now I need to go through and I need to check the second one. All right, so it's going to be my j component here. So the partial of p with respect to x is going to be the first one. All right, so partial of p with respect to x, that's going to be y cosine of z. And then I'm going to take my, again, j component, partial of m with respect to z in this particular case, because this times this. So partial of m with respect to z, that's going to give me y times cosine of z. Once again, these partial derivatives are equal to one another. Working with the last one, all right, that's going to be the k component, partial of p with respect to, sorry, I lost track here. The last component, oops, not p. Cheese and crackers. Here we go. Perfect. All right, the last component. This is going to be the partial of n with respect to x. Here we go. So partial of n with respect to x, that's just sine of z. And then that must be equal to the partial of m with respect to y. So partial of m with respect to y, it's just sine of z. which means they are equal to one another. Nice. So what we can say at this point in time is f of xyz, f of xyz is a conservative vector field. Nice. So again, we're all happy and excited once we actually get to that vector field that we're going to be looking for. All right, awesome. Now, what we want to focus on then is we want to focus on how to find these potential functions. All right, so now that we know how to check whether a vector field is a conservative vector field or not, we now want to process to find these potential functions. All right, so what we're going to do is we're going to start by looking at one of the definitions. All right, so if f is a conservative vector field, then there exists a potential function f such that the vector field is equal to the gradient of f. All right, and this is what we want to work with. All right, this is what we want to work with to make sure that we can find these potential functions. Because if this is equal to one another, then let's see what's going to happen. All right, so what I want to do is I want to start by defining my vector field, my potential vector field. So let's go ahead and let's let f equal to p in the I direction plus q in the j direction, and let this be a conservative vector field. Just like such. Nice. All right, and what we're going to do at this point in time, since it's a conservative vector field, we're going to find this potential function. So I'm going to say let f be the potential function for f, all right, for that vector field that you found. All right, so we're going to kind of keep that in our back pocket. All right, now since we have this conservative vector field, and since we know that because we have this conservative vector field, we have this potential function, we know that this equality is going to hold, right? But we also know that the gradient of f is just going to be the partial of the function with respect to x and the partial of the function with respect to y, again, respectively in component form. So what does that give us and how does that benefit us? Well, this benefits us in this way, that if I'm looking at my gradient vector field, or in this case my potential function in form of a vector, all right, I'm really looking at this piece right here for this conservative vector field, which is f. Now, what does this tell us then? Well, this tells us component-wise that the partial of that potential function with respect to x must be equal to my function p. And it also tells us that my derivative, partial derivative of my function with respect to y, must be equal to the y component on my conservative vector field. And again, once we have these, then we're able to build everything that we need about this. Because now, can we solve these specific equations for f? In other words, can I take a antiderivative on both parts? Sure we can. All right, we can take a partial derivative of this function p with respect to dx, and that should give us our potential function. Same thing here. If we want to find this function, all we do is take an antiderivative for that function q with respect to y. And in that sense, we're then going to be able to discover what is that potential function that we're looking for. All right, so if we have a conservative vector field, then we're able to find these potential functions. And this is the key that we need for today. All right, awesome. So what we're going to do now is we're going to find some potential functions with this new added feature that we just observed. So here goes the example. This is going to say to find a potential function for the vector field, or let's say for the conservative vector field. So now that we have a method to check whether a vector field is conservative or not, that method was right up here. That's what we were doing up here. So we have the method to know how to check whether a vector field is conservative or not. Now that we're given this conservative vector field, what we want to do is we want to find a potential function for it. All right, so here goes my first vector field here. Let's say f of x, y, and this will be 2x cubed y to the fourth plus x, that's in the I component, plus 2x to the fourth y cubed plus y in the j component. All right, awesome. So what we can do is we can verify first. All right, you can verify that this is a conservative vector field, but since we're already given that it is a conservative vector field, then what I want to do is I just want to use that fact. So what I'm going to do here is I'm going to say since f is conservative, we know that there is some potential function equal to the vector field. Now, what does that tell us then? Well, that tells us for this part up here, this is going to tell us that the partial derivative of my potential function with respect to x is going to be equal to p. But in this particular case, p is 2x cubed y to the fourth plus x. All right, so when I do this at this point in time, I now want to go ahead and I now want to solve for this specific function, which will be my potential function. So 2x cubed y to the fourth plus x. So again, I'm going to differentiate both sides. Excuse me, I said differentiate and I meant integrate. So I'm going to have here, I'm going to integrate 2x cubed y to the fourth plus x, and this is going to be dx, like such. So when I do this here, I get that my potential function, let's see, we're going to integrate this with respect to x, so that's going to be x to the power of 4, y to the power of 4, and then we're going to divide by 4, so that's going to be 1/2. There we are. Plus, same thing here, 1/2 x squared. Now, since this is an indefinite integral, what I have to do is I have to account for that. Alright, so it's my indefinite integral, and my indefinite integral, or this integral, its differential was dx, which means that when we take this derivative here, we could have some sort of constant. Alright, if we had some sort of constant, call it like a numerical constant, when we take the derivative, we're right up here. Well, the case is also that because this is a first order partial derivative, a constant could possibly look like a y variable. So what I'm going to do in here is I'm going to attach some sort of constant, but this constant is just going to be some value or some function that we can define in terms of y. If it doesn't have any variable y's, then we'll be able to find that it's a numerical value. Alright, so we must always account for the constant of integration. and because this was with respect to x, which means that if I have some y value, then naturally it goes away when I take the derivative with respect to x here. All right, awesome. So now that I have this is really good, because at this point in time, I now have my potential function. The only thing that I need to do is I need to figure out what this constant is in terms of y. All right, so what I'm going to do now is I'm now going to take the derivative of this function. All right, I'm going to take the derivative of this function. I'm going to carry it over here. So really quickly, I'm just going to list it again. 1/2 x to the 4th y to the 4th plus 1/2 x squared plus g of y. And I'm going to take that derivative again. So partial derivative, and now this time I'm going to do this partial derivative with respect to y. And there's a reason why I'm doing this partial derivative now with respect to y. Number one, it's going to isolate this specific function, or this function that might be a constant with respect to x. But more specifically, look right up top. I have that the partial of my potential function with respect to y is equal to q. So when I take this function here, partial derivative with respect to y, so with respect to y, drop that 4 forward, that's now going to be 2 x to the 4th y cubed. There we are. With respect to y, that goes away, but this function with respect to y, that's just g prime. Because again, this is a one variable function. Since it's a one variable function, we can just account for it as a derivative here. All right, but according to the work that we did up here, according to that work, we have that the partial of this function with respect to y is equal to q. And for us, q is this second component for this vector, which means this must be equal to 2x to the 4th y cubed plus y. Again, this was q. Now that's, for us, is pretty good, because in this particular case, if both of these are equal to one another, look at this. 2x to the 4th y cubed, they're going to cancel, which means all that we're going to be left with is that g prime of y is equal to y. So all we have to do now is just go ahead and integrate. So let's go ahead and integrate, that way we can solve for g of y. So when we integrate g prime of y, this is actually going to get us just g of y. All right, this is dy. So that's the integral of y dy, which is just 1/2 y squared plus some type of constant. Now this constant here is just a numerical value. Because our initial process was to find that constant with respect to y, and we did. It is an actual function that's treated as a constant back in this particular operation for my potential function. And upon further investigation, we're able to find that specific function. So what is the potential function now? So I'm going to write this here. The potential function is, and this is going to be f of x, y, it's going to be 1/2 x to the 4th y to the 4th plus 1/2 x squared plus this g of y, and this g of y, we found it to be 1/2 y squared plus c. All right, that was our g of y that we were initially looking at. Which means this is my potential function right in here. And that's awesome because, again, if we have a conservative vector field and we define a path on it and we want to go ahead and evaluate some specific path around that integral, or sorry, some specific line integral across some path in that conservative vector field, then all we really need to do is just evaluate the the endpoints through this given function, and that'll be it. Now this again is really nice. You can go through and you can verify. If you take the partial derivative of this with respect to x, then naturally you should get the first component of the vector field. Take the partial derivative of this potential function with respect to y, and you should get the second component of this vector field. Alright, so finding potential functions is really super, uber, duper important for us. Alright, so we're going to do a next example, and the next example we're actually going to use R space 3 to try to figure out what is this potential function that we're looking at. Alright, so here we have our next example, and again this example still has the same prompt that we found up here, so it says to find a potential function for the conservative vector field. Alright, so this vector field is conservative. Alright, you can go through the methods that we defined earlier to verify that it is a conservative vector field. Alright, but for the purposes that we're going to be working with, we just want to make sure that we can find this potential function. Alright, so I'm going to go through and I'm going to start identifying a few pieces here. Alright, so the first piece that I'm going to do is I'm going to identify here, this is going to be that P of xyz is going to be 2x times cosine of y minus 2z cubed. I'm going to identify q of xyz, q of xyz to be equal to the middle function here, so it's going to be q of xyz. This is 3 plus 2y e to the x minus x squared sine of y. And I'm going to identify r of xyz to be equal to y squared e to the x minus 6x z squared. Alright, perfect. So what I'm going to do now is I'm going to start applying. Well, since this is a vector field, alright, since F is a conservative, I spelled conservative wrong, is a conservative vector field, what we're going to have here is that the partial of my potential function with respect to x is going to be equal to p. We're going to have the partial of my potential function with respect to y is going to be equal to q, and we're going to have that the partial derivative of my potential function with respect to z is going to be equal to r. Right? And again, this is just by the definition for the conservative vector field. Now, if that's the case, then I'm going to say that my partial derivative for my potential function with respect to x is going to be equal to this piece here, which is p. So it's going to be 2x times cosine of y minus 2z cubed. And again, this was p that I have here. Awesome. So I'm going to go ahead and take the integral here. So taking the integral of both sides with respect to x, this is going to get me that my function, my potential function, is now equal to the integral of 2x times cosine of y minus 2z cubed. And again, that's with respect to dx. So let's go through. Potential function. This is now going to be x squared multiplied by cosine of y minus 2x z cubed. And then I'm going to have plus, I'm going to have this new function. Alright, and again, because this is a an indefinite integral with respect to x, and my potential function might include some variables that have x, y's, and z's, I need to account for this new function, call it g. This is going to have some variables that could have, or that could contain, sorry, not x and y, but this could contain variables other than x. So it could contain y, or it could contain z. And if it doesn't contain y and z, then it can possibly contain a numerical constant. And again, we need to account for that. So what we have here so far, that's great. All right, looking good so far. So I found my potential function. At least I found the skeleton for what it looks like. Now I need to go further. All right, so what I'm going to do here is I'm now going to start with this function, and I'm going to go through and I'm going to say, well, if I can take the derivative, I can take the derivative either with respect to y, or I can take the derivative with respect to z, one or the other. All right, so let's see where we want to go then. All right, I'm going to keep going here. So I'm just going to take the partial derivative of this function with respect to y. Let's just take it in a nice increasing fashion, x, y, z. All right, so then that partial of this function here with respect to y, so that first derivative here, so that's going to be negative x squared sine of y minus partial with respect to y, nothing here, but there is a derivative here. All right, so I am going to take a derivative, I'm going to take a partial derivative with respect to y for this piece of the function, g of y, z, like such. All right, now all of this must be equal to what we have here. It must be equal to q. Well, what is q? Well, let's go ahead and let's look at that. Sine y minus the partial of y for g of yz, there we are, is equal to q, and q is that middle function, which is 3 plus 2 y e to the x minus x squared sine of y. Now if you notice here, the x squared sines y's are going to cancel, and we're going to be left with this function here. So I'm going to say the partial of this function g with respect to y is equal to, and I'm going to subtract that negative over here. So that's now going to be negative 3 minus 2y e to the x. There we are. All right, looking pretty good so far. Let's go ahead and let's figure this out really quick. All right, so here we go. Now I just realized I made a mistake as I was working through some stuff ahead. I realized here I've made a mistake. When I took the derivative of g of yz with respect to y, I accidentally put a plus here. Or sorry, I accidentally put a minus, and it's supposed to be a plus. All right, so that was my apologies here, which means that this here is just supposed to be positive. There we are. So that was the only minor mistake there. Now I'm going to go ahead and integrate both sides with respect to y. That way I can go ahead and I can solve for my function y of z, in this particular g of y and z. So I'm integrating this function 3 plus 2y e to the x with respect to y. So here we go. This is now going to be 3y plus y squared e to the x plus, I'm going to have a new function now. My new function, I already used f, g, so I'm going to use h. The new function will have some sort of constant. It cannot have the variable x because we already took care of that when we took the partial of f with respect to x. So it cannot contain x. It cannot contain a variable for y because we just found all those variables for y, which means this function must contain at most some variable that contains z. All right, now could it be a numerical constant? Yeah, sure it can. All right, but at this point in time we have no idea, so we're going to keep going. All right, so just to recap what I have so far, my function f so far is x squared times cosine of y, and I'm getting this from right above, minus 2xz cubed plus no longer g of yz, because again we just solved a little bit more explicitly there, so that's 3y plus y squared e to the x plus sum h of z. All right, so this piece came down here, and I also used this part right in here. Awesome. So what I need to do now is I just need to figure out what is this final constant. What is that final constant of integration with respect to z? So what we need to do then is we need to take the partial derivative of this function with respect to z. So let's go ahead and do that. First term goes away. Second term is going to be negative 6xz squared. All right. Third term goes away. Fourth term goes away, and the last term is just going to be the derivative, in other words, h prime of z. But all of this must be equal to, by definition, because of a conservative vector field, it must be equal to r. So then what does that look like? Well, this now looks like negative 6xz squared plus h prime of z is equal to r, and r was that y squared e to the x minus 6xz squared. Notice the negative 6xz squareds are going to cancel, which means we're only left with h prime of z is equal to y squared times e to the x. All we have to do now is integrate. So we're going to integrate with respect to z, and that's y squared e to the x, and this is going to be with respect to z. When we get this, all right, this is going to have, again, some sort of z component that we have to be looking at. All right, so here we go. All right, so this should get us z times y squared e to the x. And then at this point in time, then we should naturally just get some sort of constant. So the potential function that we have is equal to x squared times cosine of y minus 2xz cubed plus 3y plus y squared e to the x, plus we're going to have this h of z, which we just found to be z y squared e to the x plus c. And this is that potential function that we're looking for. So this process we're going to have to repeat over and over and over again until we can understand what it means to be that potential function and to find that potential function. All right, so I hope you all enjoyed this lesson, and I do believe that now wraps it up for these line integrals and the fundamental theorem of line integrals that we work with. All right, so I will see you all for the next lesson.